We can see this going on in images. So here's a nicer picture showing you aliasing in images. So you can see what's happening is that this is a radial sine wave. And you can see as you get closer and closer, the pixels are supposed to be wiggling faster and faster. And eventually, I run out of pixels. Okay, I don't have enough samples to get how quickly the thing varies. And so that's an example of aliasing here. So what is its impact on you? Well, its impact on you is you have to be a little careful how you treat your images. For example, and this comes from Steve, all right? Suppose I've got this image, a beautiful Van Gogh picture, and suppose it's too big to fit on a screen. I want a smaller version of it. How can we reduce it? I don't know, make it half the size or a quarter of its size to do that. Well, one obvious way would be to throw away every other column and every other row, right? Just throw those away. And that's called image subsampling. Now, by the way, here it says by half. What it means is I throw away half the columns and half the rows, which of course is actually a quarter size smaller, right? But half meaning half the rows, half the columns. If I did that again, I would now have 1/4 the total rows, 1/4 the total columns, 1/16 the size. I could do it again, 1/8. In fact, you might start to notice that this is already looking a little ugly. And in fact, to make it clear exactly how ugly it is, let me blow up the half, the quarter, and the eighth by zooming in on both of them, just blowing up the pixels. And you'll notice this is atrocious, okay? The 1/2 one doesn't look too bad, but remember here, we've only taken 1 out of every 8 columns and 1 out of every 8 rows, and then we blew the thing back up. And you can see that this does not look like a blurry version of the original, okay? And the reason is we have aliasing. We have sampled too infrequently for the amount of variation that there is. Essentially, things wiggle in here more often than 1 out of every 8. And so if I just take 1/8, right, I'm not capturing all the wiggles. So what's the right thing to do? Well, we need to do that anti-aliasing. We just learned that. So a simple one is to do Gaussian, okay? So what we'll do is we'll filter, right? So we'll take the Gaussian and then take every other row, all right? And then if you want to be not so clever about this, you could do a Gaussian of that and take every other row of that to get the 1/4. And you could do the Gaussian again and do that. Or what you could do is you do a much bigger Gaussian to begin with and take 1 out of every 8. You can convince yourself that mathematically these are going to be equivalent. When I do that and I blow up the Gaussian 1/8, you'll see that this actually looks pretty much like a blurry version of that, right? Compare this to what we did with the subsampling, right? So here's sort of our original. Here is the Gaussian 1/8 4x zoom, and here is the subsample 4x zoom. And you can see that the Gaussian does a much better job in doing the reduction, and that's because it's been anti-aliased. So if you're doing computer vision and you decide, you know what, I've got this huge 1920 by 1080 image coming in, but I'm just trying to recognize faces, right? And my faces are going to be, 100 pixels big, let's say. And you say, you know what I can do is, it's going to be expensive to do that face recognition. We're going to talk about face recognition towards the end of the class. It's expensive to do that over the entire image when it's so big. Let me make the image, 1/8 its size this way, 1/8 its size that way. And I'll make my faces smaller and look for them that way. You know what? That will work pretty well if you do this, if you do anti-aliasing. If you just pull out the arbitrary pixels, right, you're going to make a mess of the whole thing. You'll get aliasing, and then the faces won't look right. So that's why doing this kind of stuff matters even in computer vision.